Now let's go ahead and solve the symmetric tree problem on LeetCode. In this problem, we're given the root of a binary tree and we need to check whether it's a mirror of itself, i.e. it's symmetric around its center. So if we were to fold this tree along its center axis, then the structure and values on the left would be identical to the structure and values on the right. Two conditions we need to check for it to be symmetric, like I said. The structure has to be the same on both sides, and similarly their values have to be identical. So to the left of 1, if it's 2 here, which it is, we need to have on the right a 2 as well. If we had a 3 here and a 2 here, then it's not symmetric, even though they may have the same structure. We're going to solve this in 2 different ways. The first method, which is more optimized and much quicker, we'll do that first. And then the second method, which is how I solved it initially, and I'm quite proud of it, so we'll check out the second method in a bit. But the second method, we're going to solve it through level order traversal. So the first thing I'm going to check is if the root they gave us is equal to null before we do any recursion whatsoever. And if that's the case, then we're going to return true because an empty tree is symmetric. And then we're going to return the result of a method that we're going to create in a second that takes 2 inputs, 2 tree nodes, which are root dot left and root dot right. So the idea is I'm going to check if we're at 1, I'm going to check if root dot left and root dot right have the same structure and contain the same value. If that's the case, I'm going to recursively call our method to check for these nodes' children. And the way we're going to check recursively is I'm going to check if this node dot left is equal to this node dot right, and then I'm going to compare this node dot right to this node dot left, and if everything returns true, then we have a valid tree. So let's go ahead and create our helper method now. It's a public, it's going to return boolean. We called it check symmetry. It takes 2 parameters, tree node that's called T1 and tree node T2. And now since it's recursion, we need a couple base cases. The first thing we're going to check is if the nodes that we're on are both equal to null, then we're going to return true. So if T1 is equal to null and T2 is equal to null, then return true. The second condition we're going to check is if T1 is equal to null or T2 is equal to null, then return false. And the final condition we're going to check is if T1.val is not equal to T2.val, then return false. So let's take a look at each condition very quickly. If T1 is equal to null and T2 is equal to null, remember we said up here that an empty tree is symmetric. Therefore, if T1 is null and T2 are null and both sides are empty, then we're going to return true, then it is symmetric. If one of them is null and the other is not, then we're going to return false, obviously. And finally, if the value which we're on of the left node is not equal to the value on the right node or whatever node, then we're going to return false, because remember I said we have to check if it's symmetrical based on structure and value. So finally, what we're going to do is we need to recursively call our function to check for to scan through the entire tree. So what we're going to do is we're going to return check symmetry. Like I said, we need to compare left with right. So if we were here, left with right, and we need to also check right with left. So return check symmetry of what? T1 dot left and T2 dot right. Also, we need to check symmetry of T2 or T1 dot right and T2 dot left. So let's submit this code and see if it works. Alright, perfect. Before we move on to the second method, let's actually go ahead through an example just to make sure everything makes sense. Also, obviously, the second method, you don't need to stick around for it, so this is more important. Alright, so if root is equal to null, let's take example 1. Okay. If root is equal to null, is it? No, it's 1. So we skip this. Then we need to return check symmetry of root.left and root.right. So what's going to happen is we're going to call this function here. Let's go ahead and write these down. So tree node T1 would actually be root.left, which is 2. And tree node on the right would also be 2. Let's see what happens here. Is T1 null? No, it's not. Is T2 null? No, it's not. So we don't need to return true. Is one of them null? No. Is the value not equal? Is the value of root.left, which is 2, not equal to the value of root.right, which is 2? That's also not the case. So we need to actually call this statement now. And we need to check T1.left. So what's to the left of our 2 on the left? That's 3. What's on the right of our node on the right, which is also 3? So we need to check this. And at the same time, we need to check T1.right. So that would be 4. And T2.left, which is also 4. Okay, so before we do this, let's see what this will give us. So let's take this, put it here. Let's go ahead and go through our code once again. Are both values or one of them null? No, no. So we can check this condition. Are the values not equal to each other? Also no, so we can skip this. Then we need to return this. So let's take it and see what happens. So we need to check, where are we? We're on 3. So we need to check the left of 3 with the right of this 3. So that they're both null. So null and null. And check symmetry of T1.right. So that's the 4 on the right is null. Also we need to check the right side of this node. So 3.right, that's also null. And T2.left, so the left of 3, which is also null. So if we go through our code, since both of them are equal to null, we go here. Is T1 and T2 both equal to null? Yes, so return true. So this would be true. And this would be true as well. True and true, that's obviously true. And then we can just replace this right here since we found its result with true. And we can remove this. And now we can check symmetry of 4 and 4. So let's go ahead and do that. So if we're here at 4 and 4, are they both equal to null? No. Is one of them equal to null? No. Are their values not the same? No. So we return this statement. And then we need to check to the left of 4, which is null. And to the right of this 4, which is also null. And we need to check to the right of this 4, which is null, and compare it to the left of this 4, which is null. And so null and null, that's true. Null and null again, that's true. True and true, that's true. So we know this is true, and we can replace this with true. True and true, that's true. And so the result of our first return check symmetry statement is true. Okay, now let's solve it through the level order traversal way. If you're not familiar with level order traversal, I will link the video which I created explaining level order traversal. But if you don't want to watch that, that's completely fine. I'll try my best to explain it as we go along. So actually, first of all, I'm going to write the original code for level order traversal, and we'll go through it line by line. But then I'm going to make some modifications to our code, and I'll explain why as when we get there. So the first thing we do in a level order traversal is we're going to create a list of list integer, and we can call this result, which is equal to new array list. What we're going to do is we're going to store in a list of list integers the elements in each level. So for example, our result list would look like this. We'd have 1 on its own, and then we'd have 2 on its own, and then we'd have 3 4 4 3 on its own. This is what our result array will look, our result list would look like. So let's delete that and keep going. So to do that, we need to first create a queue, an empty queue. So queue which stores tree node. Let's call this queue is equal to new linked list. But the first thing we're going to put in our queue is queue.add the root value which they gave us in the given. So the reason we use a queue is because we want to add elements from left to right, and also we need to process each element's children, and we need to do that in a certain order, and since cubes are first in first out, we can do just that. So now what we're going to do, also I would go through this example to see what our level order traversal list would do. It would make more sense. But what we're going to do now is we're going to check if our queue is empty, or we're going to do a certain block of code a amount of times until our queue is becomes empty. And you might be saying, well, our queue only has one root, which is correct, but throughout this code we're going to process the root's children, and we're going to keep adding elements into a queue until there's no more elements to add, or until the queue becomes empty, in other words. So while the queue is not empty, what we're going to do is we're going to create an int level size, which updates with each iteration, is equal to queue.size. This will help us iterate through the number of elements in each list. So since here we have like 2 elements, we won't surpass 2, and we just stay on this level. It'll make more sense as we go along. And then we need to create a list of integer, which is actually where we're storing our elements in each level in order to add them to our result list. So list integer, we can call this current level is equal to new array list. Okay, now what we're going to do is we're going to loop through our level size. We're going to loop through the number of elements at each level. So for an int I equals to 0, as long as I is less than, what was it called, level size, I++. What we're going to do is we're going to create a tree node. We can call this node, which is equal to queue.poll, meaning the very first element that we put in our queue, we're going to remove it from that queue and put it in the node. So now in the first iteration, our queue would be empty. We remove the first element in our queue, we put it into node. Then what we're going to do is we're going to add the value of that tree node, which is stored in node, into our list of integer called current level. So current level.add node.val. Then what we're going to do is we're going to check if node.left is not equal to null. Then we're gonna add this to our queue, node.left. And then if node.right is not equal to null, then queue.add node.right. And then finally we just need to add our current level to our result array, which we created in the very beginning. Okay, so let's go through this example to see what we're doing, and so it all makes sense. Very first thing, we create an integer called or a list of this integer called result, which we're going to store the elements of each level separately. And then we're creating a queue because we want to take advantage of the fact that queues are first in, first out, and we want to place the values in our result list of list integers from left to right and process their children in the correct fashion. So the first thing we're going to add to our queue is the root, which is 1. Currently our queue is filled with just 1. And is our queue empty? No, it's not. Contains 1. So retrieve or create an int called level size, which is equal to queue.size, which is just 1. And then create a list of integers called current level, which we're going to add the elements of each level in. Then we're going to loop through the number of elements on each level. So I here would, as I is equal to 0, I less than 1, I plus plus. Remove 1 from our queue and store it in a tree node called node. Then add the value of node to our current level list. So our list of integer called current level now would contain this. And then we're gonna check if node.left, so 1.left, which is 2, is not equal to null. Is it? No, it's equal to 2. So we add to our queue 2. Now our queue looks like this. And then we're checking if 1.right, which is also 2, is not equal to null, which it's not. Add the queue.add node.right, which is also 2. And then we go back up here, or before we go up here, we need to add the result of current level. So our result array would look like this. And then we take these this queue, which I just deleted. Our queue now, is it empty? No, it contains 2 and 2. Queue.size, that's 2. We create a new, we're gonna overwrite these 2. So now this is empty once again, and this is equal to 2. Then we're gonna iterate through the elements on that level. We're going to remove the first element, which is 2, and store it in node. Then we're going to add the value of our node, so 2, into a new empty current level list. And then we're going to check if node.left is not equal to null, which it's not. So we're going to add 3 to our queue, and we're going to check if node.right is not equal to null, so to the right of 2, which is 4. But we're not done, because we're going to continue this for loop, I equals 1. We're going to remove the other node in our queue, which is 2. So actually after we complete this one, what our queue is going to look like is this: 2, 3, 4. And then we're going to remove 2 from this function, queue.pull, and we're going to add its value to our current level. So it would so now our current level would look like this. There's already 2 from before, and now we just added a new 2. So we can just delete that. And then this would look like this. And then we're checking if 2.left is not null, it's equal to 4, and 2.right is 3. So we're going to add them to our new queue. It's going to look like this. Then we're going to add current level, which contains 2 and 2. And we're going to go on with our queue. So this would go back up here, and we'd keep going until it terminates. This may not have been the best example, but I'm trying to go quickly so we can solve this problem. So like I said, I'm going to link the video to my level order traversal problem in this video. Go ahead and watch that to just really understand what's going on. So now we need to make some modifications to our level order traversal in order to solve this problem. Because null spots matter, missing spots matter, what we're going to do is we're going to delete these 2 statements. And after this code, we're going to check if node is not equal to null. If it's not, what we're going to do is we're going to add to our current level the value of that node, so node.val. And then we're going to add to our queue the left and right children of that node, so node.left and node.right. Otherwise, if the node is null, we're just going to add null to our current level. So we can delete this, and then we added all the elements within our level into current level, all the elements of the level that we're on. Now what we're going to do is we're basically going to compare. So for example, if we're on this level 2 and 2, we're going to compare the first element to the last element. If they're the same, that's good for us. If they're not the same, then they're not symmetric. And we're going to do that for every tree. So we're going to check if this element in our list is equal to this element in our list, and then we're going to check if this element is equal to this element. So let's go ahead and do that. So for every list of integer, let's call it level, in our result, what did I call it? Result or res? in our result list of list integers, int x equals to 0, because we need to check the first element and the last element. So to check the last element, we need a pointer to the last element. So int y is equal to level dot size minus 1, since indexes start at 0 in Java. Then while x is less than y, because we don't want to so if x is pointing at 4 and y is pointing at 4, the next iteration, once we do x plus plus and y minus minus, obviously to keep the while loop going, we're going to go through cases we already checked and we don't want to compare those. So while x is less than y, if level dot get the value at x is not equal to level dot get value at y, then return false. And then we need to do x plus plus y minus minus. And then if we go through all these cases, if we keep x plus plus y minus minus and this is always true, then what do we need to do? We need to, right here, return true. So let's run this code and see if it works. So we just had an extra bracket here which I deleted, but there you go. That's the second solution. As you can see, not very optimized, but it works nonetheless. So I hope you found that video helpful. That was the symmetric tree problem on LeetCode, and thanks for watching.